Welcome to solverfy.
So again, we're told to determine the x-coordinate of the centroid of the volume shown. This volume was obtained by intersecting an elliptic cylinder with an oblique plane. And again, they tell us to think about this as a depth, because this plane is x varies linearly with y, and so we could think about this as depth. But again, I think it's best just to do the math, and it's not that hard to do the math. Because we can look up a lot of things that we don't actually have to do the integrals. So, we don't know what the angle this plane makes. So it has a slope a, and we know it's just a function of x, because it slices it with this a plane that's slicing up through here. So we call that angle, that slope a. And so y1 equals a of x. Now, one thing we need is what I call S, is the first volume moment. Right? So the first moment of volume in the x direction. I suppose I should label this with an x. So we can do that, and one thing we can do is see that, okay, dv is dy dA, right? And we know y is a function of x. So we can do this integral, and so we just get, we wind up with ax squared dA, right? And this is kind of using what they were saying to look at it as a pressure, but it's just doing the math and just being clever about some things. So if we have ax squared dA, well, that looks like an area moment, which it is. And so that's the area moment over this ellipse, or a times that area moment about this axis. Okay, so we can look up what that area moment is. And then we need the volume. And so the volume is the integral of 1 over dv, and so that's dy dA, where y goes from 0 to y1 of x, and then the area of the ellipse. So then this just becomes, in here, we do this inner integral, it becomes ax, so we get the integral over the ellipse of ax dA. Well, that is simply the, so we can pull the a out here, and x dA is simply x bar of a, of the area of the ellipse, times the area of the ellipse. Okay, it's just by the definition of the centroid. So we can look that up. Well, we can just figure it out. The centroid of the ellipse is at a distance, I call it h, but it's 64 millimeters. Right? So we know that, and we can look up the area of the ellipse. And so the area of the ellipse is pi hb, where again this is b and this is h, so the major axis length and the minor axis length. And then we can look up IC here, and that is simply about the centroid of the ellipse. It's 1/4 pi h cubed b, and then we need to use the parallel axis theorem that says that we'd have to add a times the distance x bar a, and that's h squared. And that just simplifies down to 5 pi over 4 bh cubed. And then the volume, we can just take the area times a times h, so we get a b h squared times pi is the volume. And we can then figure out that we know that x bar is Sx divided by the volume, Sx is a times I about the z-axis, and then we have over the volume. And we know we can plug everything in here, and what we see is that this A cancels with this A, so it turns out that it actually doesn't matter what this angle is. Where the centroid is in the x direction doesn't matter what that angle is, which is kind of interesting. But what we get is it is 1.25 times h, and h is 64 millimeters, so the position of the centroid in the x direction is 80 millimeters away from the origin. So it is somewhere, so this would be 64, and then we need to go, what, 16 more, so somewhere in here, which we'd expect. Again, it's going to be past here, because if it was just a full ellipsoidal cylinder, then it would be at 64, but because of its slope here, but interestingly, it doesn't depend on the slope. So obviously, if A is 0, then things break down, because then we have a volume of 0.